we have discussed applications of Taylor and Maclaurin series to representing functions, to representing integrals. In this example, I want us to look at applications of these series to computing limits. So let us evaluate the limit. As x goes to 0, e to the x minus 1 minus x over x squared. So it is not hard to check that for x equal to 0, we have 0 both in the numerator and in the denominator. And so this is an indeterminate form 0 over 0. So the way to apply a series to evaluating this limit is the following. Recall that we know the Maclaurin series for e to the x, which in this case will be useful because Maclaurin series represents a function, in this case e to the x, around the center 0, and the limit we want to evaluate here is precisely when x goes to 0. So somehow it makes sense that if we want to evaluate a limit when x is close to 0, it is natural to apply Maclaurin series, which gives a representation of e to the x when x is close to 0. So using this fact, using the Maclaurin representation, we can rewrite our limit as follows. So we have in the numerator e to the x. Let's replace e to the x by its expansion. So if you go back and check your notes, e to the x has the following expansion. It starts with 1 plus x divided by 1 factorial, that is 1, plus x squared divided by 2 factorial, plus x cubed divided by 3 factorial, and so on. So this is an infinite power series that starts off like so. And then we will subtract 1 and x and divide this difference by x squared. Great. Now observe that the terms 1 and x, which are part of our infinite series, will cancel with the terms that are being subtracted here, which results in limit as, oh, it should have been 0, of course. Limit as x goes to 0. In the numerator, I have part of my series, which starts now with x squared over 2 factorial, the two first terms being cancelled out already, plus x cubed over 3 factorial, plus and so on. We won't need the subsequent terms, but there are infinitely many of them. Everything divided by x squared. So now we can cancel off the x squared with the terms in the numerator, because all the powers of x involved in the numerator are 2 or higher. So we can cancel the x squared with x squared here with x cubed and so on. Every power of x involved in the numerator is at least 2. So that gives us the following expression. After cancelling the x squared, we have 1 over 2 factorial plus x over 3 factorial plus all the subsequent terms. So all the terms here will contain x. Right, but the limit here is now evaluated of an expression which is a power series. This is a power series which apart from the first term, vanishes at 0. So it doesn't have any problems at 0. We can just substitute x equals 0 into the power series to evaluate the limit, and we'll get 1 over 2 factorial since all the subsequent terms vanish, because they contain x, and when we substitute x equals 0, we get 0 for all of these terms. And so we have computed our limit to be equal to 1/2. So it is interesting to compare how this works out as compared to the standard method, which in this case would be applying L'Hopital's rule. So you would have to apply L'Hopital's rule twice to arrive at the same answer. So if you're proficient with series and you remember the expansion for e to the x, using this approach to evaluate the limit may even be faster.